Good evening, and welcome to the Calm Cosmos. This channel is a gentle corner of the universe where you can let go of the day, close your eyes, and drift into sleep while listening to peaceful stories of science. Tonight, we're venturing into one of the most mysterious frontiers in all of physics. What is the quantum realm? It sounds simple, but hidden within that question lies a story that stretches from curious experiments to profound mysteries, from the tiniest particles to the nature of reality itself. Before we begin, I'd love to know where in the world are you listening from tonight. It's always fascinating to see how far and wide these stories travel, and if you find these videos help you to relax or spark a little curiosity before sleep, I'd be grateful if you could give the video a like and subscribe to the channel. If you're already subscribed, thank you so much for your support, and if you haven't yet, please do click the notification bell so you don't miss the next journey we take together. I like to think of these videos as both lullabies and lessons, though I hope this one isn't so interesting that it keeps you awake. But if it does, at least you'll drift off having learned a little about the hidden fabric of reality itself. So then, what is the quantum realm really? Is it a place where particles exist? Or is it a description of how nature behaves when we look closely enough? Let's step quietly into that mystery. The quantum realm is not something we can touch or hold in our hands, yet it defines everything we experience. Every heartbeat, every sunrise, every device we use takes place because of it. And yet the nature of the quantum world is far from obvious. To ancient thinkers, matter was continuous and predictable. To classical physicists, particles had definite positions and moved along clear paths. To quantum physicists, everything became uncertain, probabilistic, and strange. In this video, we'll trace the journey of that idea, how it arose, how it reshaped physics, and how it continues to challenge us. We'll explore the wave-particle duality, the uncertainty principle, quantum entanglement, and the puzzles of measurement. We'll look at attempts to understand what quantum mechanics really means, and even ask whether the quantum world might one day prove to contain hidden variables we haven't yet discovered. Along the way, we'll pause for thought, philosophical reflections on whether particles truly exist before we measure them, or whether reality itself is created by observation. We'll look at practical ways quantum mechanics shapes our lives, from semiconductors to MRI machines to the way atoms bond to form molecules, and we'll wander into the speculative edges, quantum computers, teleportation, and the strange possibilities quantum mechanics might enable beyond what we can currently achieve. This is not just a journey through physics, but through imagination and wonder. By the end, you may not find a final answer to what the quantum realm is. No one has one yet, but you will have walked its contours from the human scale of everyday objects to the atomic scale of electrons and photons. So settle in, let your mind drift gently, and prepare to explore a question as old as curiosity itself and as fresh as the latest discovery. What is the quantum realm? Long before physicists spoke of quantum mechanics, people were already wrestling with what matter actually was. To us, it feels obvious. Matter is the stuff around us, solid and real. But if you ask what matter really is, or whether it can be divided forever, the answers become slippery. Ancient thinkers sensed this strangeness and began shaping ideas that would echo all the way to modern physics. In ancient Greece, philosophers argued about the very nature of matter. Democritus, the great atomist, believed in a universe made of tiny indivisible particles moving in a vast void. For him, atoms were absolutely real, the fundamental building blocks of everything. Cut anything in half enough times, and you would eventually reach something that could not be cut further. The word atom itself comes from the Greek atomos, meaning indivisible. Not everyone agreed. Aristotle rejected the idea of atoms and void. To him, matter was continuous, infinitely divisible. Between any 2 points, you could always find another point. Remove all matter, and there would be nothing left, not even empty space. Matter was a continuum, not a collection of particles. This disagreement, whether matter is discrete or continuous, would resurface again and again in the history of science. It frames questions physicists still grapple with today. Centuries later, during the scientific revolution, chemistry began to provide evidence for atoms. John Dalton in the early 1800s showed that elements combined in fixed ratios, suggesting they were made of discrete particles. But atoms remained theoretical, invisible to any instrument of the time. By the late 19th century, Physics had grown more precise, and new phenomena demanded fresh ideas. Electricity, magnetism, and light revealed behaviours that classical mechanics couldn't fully explain. Experiments with heated objects showed that light was emitted in specific colours at specific temperatures, patterns that didn't fit with continuous wave theories. And so, by the time the 20th century arrived, the stage was perfectly set. The ancient questions of Democritus and Aristotle, the chemical evidence for atoms, the puzzling behaviour of light and energy, all had chipped away at simple notions of matter and reality. What seemed obvious had become uncertain. Were atoms real particles or just convenient concepts? Was energy continuous or discrete? These unanswered questions hung in the air as physics approached a revolution. It was in that climate of uncertainty that quantum mechanics emerged, a vision that did not simply take sides in the ancient debate, but dissolved the old categories entirely. Matter was neither purely particle nor purely wave, but something stranger. Energy came in packets, quanta, that defied classical expectations. The answers of the ancients and the certainties of classical physics would fade into history, replaced by something far more mysterious and beautiful. In hindsight, the journey seems inevitable, as though the universe had been nudging human thought step by step toward quantum mechanics. But for those early philosophers, and for the classical physicists after them, the puzzle of what matter and energy truly were was as mysterious as ever. Their debates remind us that even the most familiar aspects of existence can turn slippery when examined closely. What feels obvious in daily life, the solidity of objects, the predictability of motion, is in fact among the deepest mysteries science has ever faced. The year was 1900, and a German physicist named Max Planck was working on a stubborn problem. When objects are heated, they glow, first red, then orange, then white as they get hotter. This glow, called blackbody radiation, had been measured carefully, but classical physics couldn't explain the pattern. The equations predicted that hot objects should emit infinite amounts of ultraviolet light, a clearly wrong result called the ultraviolet catastrophe. Planck, desperate to find a solution, tried something radical. What if energy wasn't continuous, but came in discrete packets? He called these packets quanta. By assuming that light could only be emitted or absorbed in specific chunks, proportional to its frequency, Planck's equation fit the experimental data perfectly. Planck himself was uncomfortable with this idea. He thought of quanta as a mathematical trick, not a real feature of nature. But the genie was out of the bottle. Energy, it seemed, was quantized. 5 years later, Albert Einstein took Planck's idea seriously. He was puzzling over the photoelectric effect, where light shining on metal knocks out electrons. Classical wave theory said that brighter light should give electrons more energy, but experiments showed something different. The energy of the ejected electrons depended on the color, frequency of the light, not its brightness. Einstein proposed that light itself comes in particles, which we now call photons. Each photon carries a quantum of energy. Bright light means more photons, not more energy per photon. Only photons with enough energy, determined by their frequency, could knock electrons free. This was revolutionary. Light, long thought to be a wave, also behaved like a stream of particles. Einstein's explanation worked perfectly, and it eventually earned him the Nobel Prize. But it raised a troubling question. Is light a wave or a particle? The answer, as quantum mechanics would reveal, is both and neither. Light exhibits wave-like behaviour in some experiments, and particle-like behaviour in others. This wave-particle duality became one of the central mysteries of the quantum realm. In 1913, Niels Bohr applied quantum ideas to the atom. Ernest Rutherford had shown that atoms have a tiny, dense nucleus, with electrons somehow orbiting around it. But classical physics said those orbiting electrons should spiral into the nucleus, radiating energy as they go. Atoms should collapse instantly. Bohr proposed that electrons could only occupy certain allowed orbits, each with a specific energy. Electrons could jump between orbits by absorbing or emitting photons, but they couldn't exist in between. These quantum jumps explained why atoms emitted light at specific wavelengths, creating the spectral lines astronomers had observed for decades. Bohr's model was a patchwork, mixing classical orbits with quantum rules. It worked for hydrogen but failed for more complex atoms. Still, it showed that the quantum world operated by different rules than the everyday world. By the 1920s, quantum mechanics was ready to mature. Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and others developed a complete mathematical framework. Heisenberg's matrix mechanics and Schrödinger's wave mechanics, though seemingly different, turned out to be equivalent descriptions of quantum reality. At the heart of this new physics was the wave function, a mathematical object that described the quantum state of a particle. The wave function didn't tell you where a particle was, but rather the probability of finding it in different places. Quantum mechanics was fundamentally probabilistic. This idea troubled many physicists, including Einstein. He famously said, "God does not play dice with the universe." But the experiments kept confirming quantum predictions. The dice, it seemed, were real. The birth of quantum theory was not a single eureka moment, but a slow revolution, built from the work of many brilliant minds wrestling with strange experimental results. Planck's quanta, Einstein's photons, Bohr's atomic orbits, all were stepping stones toward a new understanding. By 1930, quantum mechanics was an established framework, strange and counterintuitive but undeniably successful. It explained atomic spectra, chemical bonding, the behavior of metals and insulators, and countless other phenomena that classical physics could not. The quantum realm had revealed itself not through telescopes pointed at the stars, but through careful experiments with light, atoms, and energy. And what it revealed was a universe far stranger than anyone had expected, where particles were also waves, where energy came in lumps, and where certainty gave way to probability. The young physicists who built quantum mechanics had dared to ask, what if the rules we thought were obvious were simply not true at the smallest scales? Their answer reshaped physics forever, leaving behind a universe far more mysterious and beautiful than the clockwork cosmos of Newton. In 1924, a young French physicist named Louis de Broglie made a bold suggestion. If light, long, thought to be a wave, could behave like particles, then perhaps matter, long thought to be made of particles, could behave like waves. He proposed that every particle has an associated wavelength, inversely proportional to its momentum. It was a strange idea, but within 3 years it was confirmed. Clinton Davison and Lester Germer fired electrons at a crystal and observed an interference pattern, the telltale signature of waves. Electrons, tiny particles of matter, were interfering with themselves like ripples on a pond. This wave-particle duality became central to quantum mechanics. A photon is neither purely a wave nor purely a particle. It is a quantum object that exhibits different aspects depending on how you observe it. The famous double-slit experiment captures this strangeness perfectly. Imagine firing particles, one at a time, at a barrier with 2 slits. On the far side, you place a detector screen. If the particles behave like little balls, you'd expect 2 bright bands on the screen, one behind each slit. But that's not what happens. Instead, you see an interference pattern, alternating bright and dark bands, exactly what you'd expect if waves were passing through both slits and interfering with each other. Each particle seems to go through both slits at once, interfering with itself. Now, suppose you try to peek. You set up a detector to see which slit each particle goes through. The moment you do, the interference pattern vanishes. The particles now behave like little balls, passing through one slit or the other, creating 2 simple bands. This is not a flaw in the experiment, it is a fundamental feature of quantum mechanics. The act of measurement changes what you observe. Before measurement, the particle exists in a superposition, a quantum state where it is, in some sense, going through both slits. After measurement, it chooses one path. What does this mean? Physicists have debated it for a century. Some say the particle really does take both paths and collapses to one, only when observed. Others say there's no collapse at all, but rather a branching of reality into different outcomes. Still others suggest that the question itself is misguided, that quantum mechanics simply describes what we can know, not what really happens. The wave-particle duality forces us to abandon simple pictures. We cannot visualize a photon or an electron the way we visualize a billiard ball. The quantum world does not offer us images, only mathematical descriptions. Yet these descriptions work. They predict experimental results with stunning accuracy. Engineers use them to design transistors, lasers, and solar cells. Chemists use them to understand molecules. The strangeness of wave-particle duality is not a sign that quantum mechanics is wrong. but that nature itself is strange. Perhaps the most profound lesson is that the quantum realm is contextual. A particle's behavior depends on the experimental setup, on what questions you ask of it. In one context, it behaves like a wave, in another, like a particle. Reality at the quantum level is not fixed and absolute, but fluid and relational. This duality also hints at something deeper. Maybe our classical concepts of particle and wave are just approximations, useful at large scales but inadequate at small ones. Maybe the quantum realm operates by rules entirely its own, and our language, built from everyday experience, simply cannot capture it fully. Wave-particle duality was once seen as a paradox. Now it is seen as a clue. The universe does not owe us intuitive explanations. It simply is. And at the quantum level, it is both more unified and more mysterious than the classical world ever suggested. In 1927, Werner Heisenberg discovered one of the most profound principles in all of physics. It is impossible, he showed, to know both the position and momentum of a particle with perfect precision. The more accurately you measure one, the less accurately you can know the other. This is not a limitation of our instruments, but a fundamental feature of nature. The uncertainty principle is often misunderstood. It doesn't mean we're clumsy or that our equipment isn't good enough. It means that a particle simply doesn't have a precise position and momentum at the same time. These properties are complementary, related in such a way that sharpening one inevitably blurs the other. Imagine trying to measure the position of an electron. To see it, you need to bounce a photon off it. But the photon carries momentum, and when it hits the electron, it gives it a kick, changing its momentum unpredictably. Use a higher energy photon to pinpoint the position more precisely, and you give the electron a bigger kick, making its momentum even more uncertain. This isn't just a practical problem. Even in principle, even with perfect instruments, the uncertainty remains. It is baked into the mathematics of quantum mechanics. The wave function that describes a particle naturally encodes this trade-off. The uncertainty principle also applies to energy and time. You cannot measure the energy of a quantum system with perfect precision in an arbitrarily short time. This leads to fascinating consequences, like virtual particles that pop in and out of existence, borrowing energy from the vacuum for fleeting moments allowed by the uncertainty principle. Heisenberg's discovery shattered the deterministic worldview of classical physics. In Newton's universe, if you knew the position and velocity of every particle, you could in principle predict the future with perfect accuracy. The universe was a clockwork, its gears turning according to fixed laws. Quantum mechanics destroyed that vision. Even with perfect knowledge of the present, you cannot predict the future with certainty. The best you can do is calculate probabilities. The universe, at its most fundamental level, is irreducibly uncertain. This troubled many physicists. Einstein, in particular, never accepted it fully. His famous objection, "God does not play dice with the universe," captured his discomfort. He believed quantum mechanics was incomplete, that there must be hidden variables, deeper layers of reality that restore determinism. But experiments have consistently supported the uncertainty principle. Tests of Bell's inequalities, which we'll explore later, have shown that no hidden variable theory of a certain type can reproduce quantum predictions. The dice, it seems, are real. Yet the uncertainty principle is not a source of chaos. It creates a kind of order. Atoms are stable because of it. If electrons could have definite positions and momenta, they would spiral into the nucleus. The uncertainty principle keeps them spread out in fuzzy clouds, preventing collapse. Chemistry, biology, and ultimately life itself depend on this quantum fuzziness. The bonds that hold molecules together, the reactions that power cells, all emerge from the quantum rules that include uncertainty as a central feature. The uncertainty principle also points to a deeper truth. Quantum mechanics is not about the properties objects have, but about the properties we can measure. Before measurement, a particle doesn't have a definite position or momentum. It has a wave function, a mathematical description of potentialities. This has led to endless philosophical debates. Is reality created by measurement? Do particles only decide their properties when observed? Or is measurement simply revealing pre-existing facts, albeit in a limited way? Heisenberg himself leaned toward the former view. He argued that the path of an electron between measurements is not a meaningful concept. Only the results of measurements are real. Others disagree, but the uncertainty principle itself remains unchallenged. It has been tested in countless experiments, From particle accelerators to quantum optics labs, every test confirms it. What makes the uncertainty principle so profound is that it transforms our understanding of knowledge itself. In classical physics, the limits on what we can know are practical. In quantum physics, they are fundamental. Nature itself sets boundaries on what can be known, and those boundaries are not walls to be overcome but features of reality's deeper structure. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper arguing that quantum mechanics was incomplete. They described a thought experiment now known as the EPR paradox, after their initials. It involved two particles created together in such a way that their properties were correlated, entangled. According to quantum mechanics, if you measure one particle and find it spinning in one direction, the other particle, no matter how far away, will instantly be found spinning in the opposite direction. Einstein called this spooky action at a distance, and argued it was absurd. Information he believed could not travel faster than light. His solution was that the particles must carry hidden instructions from the moment of their creation, predetermining the outcomes of measurements. Quantum mechanics, in this view, was just ignorant of these hidden variables. For decades, the debate remained philosophical. Then, in 1964, physicist John Bell devised a way to test it. Bell's theorem showed that any theory with local hidden variables would produce different statistical predictions than quantum mechanics. Experiments could decide the issue. Starting in the 1970s and continuing to today, physicists have performed Bell tests with increasing precision. The results are unambiguous. Quantum mechanics is right. The correlations are stronger than any hidden variable theory allows. Entanglement is real. When two particles are entangled, they form a single quantum system, even across vast distances. Measuring one instantly affects the state of the other, not by sending a signal, but because they are part of a unified whole. This doesn't allow faster-than-light communication. The measurement results are random, and you can't control them to send a message, but the correlations are undeniable and instantaneous. Entanglement has moved from philosophical puzzle to practical tool. Quantum computers use entangled qubits to perform calculations impossible for classical machines. Quantum cryptography uses entanglement to create unbreakable codes. Quantum teleportation, contrary to science fiction, doesn't move matter but transfers quantum states using entangled particles. The implications are profound. Entanglement suggests that the quantum realm is fundamentally non-local. Objects separated by light years can be intimately connected in ways that defy our intuitions about space and separation. Some physicists speculate that entanglement may be even more fundamental than space itself. Perhaps the fabric of space-time emerges from patterns of quantum entanglement, with geometry arising from information shared between quantum systems. Entanglement also raises deep questions about the nature of reality. Before measurement, entangled particles don't have definite properties. They exist in a superposition of possibilities. Only when measured does the wave function collapse, and even then, the collapse is correlated across space. What does this mean for our understanding of the universe? Some interpretations, like the Copenhagen interpretation, say that measurement brings reality into being. Others, like the many worlds interpretation, say that all possibilities actually occur, branching into parallel realities. Whatever the interpretation, entanglement is a feature of nature. It's been observed in photons, electrons, atoms, and even in molecules and small diamonds. It's not a quirk of tiny particles, but a principle that scales up, limited only by the difficulty of isolating quantum systems from their environment. As quantum technologies advance, entanglement is moving from laboratories into applications. Quantum networks may one day connect quantum computers across continents using entangled photons. Quantum sensors may detect gravitational waves or map brain activity with unprecedented precision. The spooky action that Einstein doubted has become one of the most celebrated and useful features of quantum mechanics. It reminds us that the universe is far more interconnected than classical physics ever suggested. Separation in space does not mean independence. Hidden beneath the surface of everyday reality is a web of quantum correlations, linking particles, atoms, and perhaps even larger structures in ways we are only beginning to understand. Quantum mechanics works beautifully for predicting the results of experiments. Yet at its heart lies a deep puzzle known as the measurement problem. It centers on a simple question. What happens when you measure a quantum system? Before measurement, A particle exists in a superposition, a blend of multiple possibilities. An electron, for example, might be in a superposition of spinning up and spinning down. The mathematics describes both at once, with specific probabilities for each, but when you measure the spin, you always find a definite result. Up or down, never both. The superposition seems to vanish, collapsing into a single outcome. This is called wave function collapse. The problem is that the equations of quantum mechanics don't describe collapse. The Schrödinger equation, which governs how quantum states evolve, is perfectly smooth and deterministic. It describes superpositions growing and changing, but never suddenly collapsing. So what causes collapse? Is it the act of observation, the presence of a conscious observer, the interaction with a measuring device? Physicists have debated this for a century, and the question remains unresolved. Niels Bohr, one of the founders of quantum mechanics, took a pragmatic view. He argued that quantum mechanics only describes what we can observe, not what happens independently of observation. Asking what a particle really does before measurement is meaningless. The Copenhagen interpretation, as his view became known, treats measurement as fundamental and doesn't try to explain collapse. Einstein rejected this. He believed in an objective reality independent of observers. The moon, he famously said, is there even when nobody looks at it. He hoped a deeper theory would restore determinism and explain collapse as an artifact of incomplete knowledge. In the 1950s, Hugh Everett proposed a radical alternative, the many worlds interpretation. He suggested that wave function collapse doesn't happen at all. Instead, every possible outcome of a measurement actually occurs, but in different branches of reality. When you measure an electron spin, the universe splits. In one branch you find spin up, in another spin down. Both are real, but they can't interact. Many worlds is elegant mathematically. It takes the Schrödinger equation seriously, never adding collapse by hand. But it's also extravagant, multiplying universes endlessly. And it raises troubling questions. If all outcomes happen, why do we only experience one? Another approach, objective collapse theories, suggests that collapse is a real physical process, not triggered by observers but by some objective threshold, perhaps related to size or complexity. These theories modify quantum mechanics slightly, adding terms that cause spontaneous collapse when systems grow large enough. Then there are hidden variable theories, like Bohmian mechanics, which say particles always have definite positions, guided by a quantum wave. The randomness of quantum mechanics is just our ignorance of these hidden positions. Bohmian mechanics reproduces quantum predictions but is deterministic underneath. Each interpretation has strengths and weaknesses. None has been ruled out by experiment, because they all predict the same results for measurements. The differences lie in what they say about reality between measurements, and reality between measurements may be fundamentally unobservable. The measurement problem is not just academic. It touches on the nature of consciousness, the role of observers, and the boundary between quantum and classical. Why do large objects like cats and planets seem to be in definite states, while tiny particles live in superpositions? The answer likely involves decoherence, the process by which quantum systems become entangled with their environment, effectively measuring them and suppressing superpositions. Decoherence explains why we don't see macroscopic quantum effects in daily life, but it doesn't fully solve the measurement problem, because it doesn't explain why we see one outcome rather than another in a single measurement. The measurement problem remains one of the deepest mysteries in physics. It challenges our understanding of reality, observation, and existence itself. Some physicists believe the solution will come from quantum gravity, unifying quantum mechanics with spacetime. Others think it will require entirely new concepts we haven't yet imagined. For now, quantum mechanics works. It predicts, it explains, it enables technology. But it doesn't tell us what's really happening. And perhaps that's the point. Perhaps the quantum realm is telling us that our classical concepts, our demand for definite states and clear boundaries, are just approximations. Maybe reality at its core is something richer, stranger, and more subtle than any interpretation can capture. Quantum mechanics began with particles, electrons and photons, moving through space. But as physicists probed deeper, they discovered that particles are not the most fundamental entities. Instead, the universe is filled with fields, and particles are excitations of these fields. This is the realm of quantum field theory, the framework that underpins modern particle physics. In this picture, an electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. Every particle corresponds to a quantum of its associated field. Fields permeate all of space, even in a vacuum. Far from any matter, these fields exist, humming with quantum fluctuations. The vacuum is not empty but seething with virtual particles, brief flickers of existence allowed by the uncertainty principle. The first quantum field theory was quantum electrodynamics, or QED, developed in the 1940s by Richard Feynman, Julian Schwinger, and others. It describes how electrons and photons interact and makes predictions of extraordinary precision. QED calculations match experiments to more than 10 decimal places, making it one of the most accurate theories in all of science. Building on this success, physicists developed quantum field theories for other forces. Quantum chromodynamics describes the strong nuclear force that binds quarks into protons and neutrons. The electroweak theory unifies electromagnetism with the weak nuclear force, which governs radioactive decay. Together, these theories form the standard model of particle physics, a comprehensive description of matter and forces at the smallest scales. The standard model has been tested in particle accelerators like the Large Hadron Collider and has passed every test. The standard model predicts a rich zoo of particles. Quarks come in 6 types, called flavors: up, down, charm, strange, top, and bottom. Leptons include electrons, muons, taus, and 3 types of neutrinos. Each particle also has an antiparticle, identical except for opposite charge. Then there are the force carriers: photons for electromagnetism, gluons for the strong force, W and Z bosons for the weak force, and finally, the Higgs boson, discovered in 2012, which gives mass to other particles through their interaction with the Higgs field. This particle zoo might seem overwhelming, but underlying it is a beautiful symmetry. The standard model is built on principles of gauge symmetry, mathematical structures that dictate how particles interact. These symmetries are not arbitrary but seem to be woven into the fabric of nature. Yet for all its success, the standard model is incomplete. It doesn't include gravity. It doesn't explain dark matter, the invisible substance that outweighs ordinary matter in the universe. It doesn't explain why there's more matter than antimatter, or why the masses of particles take the values they do. Physicists are searching for physics beyond the standard model. Theories like supersymmetry predict new particles, partners to the known ones, that might explain dark matter. Grand unified theories attempt to merge all forces into a single framework. String theory goes further, suggesting that particles are not points but tiny vibrating strings. None of these beyond standard model theories have been confirmed yet. Experiments at the LHC and other facilities are searching for new particles, new forces, new phenomena that might point the way forward. What makes quantum field theory so powerful is its unification of quantum mechanics and special relativity. Particles can be created and destroyed, appearing from energy and vanishing again, in ways that ordinary quantum mechanics can't describe. The famous equation E=mc2 becomes concrete. Mass and energy are interchangeable, and the vacuum itself is a reservoir of potential particles. Quantum field theory also reveals deep connections between particles and forces. Feynman diagrams, simple pictures of particle interactions, show how forces arise from the exchange of virtual particles. An electron repels another electron by exchanging photons. Quarks bind together by exchanging gluons. This picture has profound implications. Forces are not mysterious pushes and pulls, but the result of particle exchanges, quantum processes happening constantly at microscopic scales. The apparently solid world around us is built from fields and their excitations, particles flickering in and out of existence in a cosmic dance. The quantum realm, seen through field theory, is even stranger than the wave-particle duality suggests. It is a layered reality where fields underlie everything, where particles are temporary, and where the vacuum is alive with quantum activity. As physics pushes toward higher energies and smaller scales, quantum field theory may itself give way to something deeper. Perhaps fields emerge from more fundamental structures, like loops or strings or networks of information. But for now, quantum field theory stands as one of humanity's greatest intellectual achievements, a framework that explains the particle zoo and the forces that govern them, all built on the strange but reliable foundation of quantum mechanics. Quantum mechanics is not just abstract theory, it is the foundation of modern technology. From the phone in your pocket to the medical imaging in hospitals, quantum effects shape the tools we use every day. The most visible application is the transistor, the building block of all electronics. Transistors work by controlling the flow of electrons through semiconductors, materials whose properties are governed by quantum mechanics. Without understanding electron behavior in crystals, we would never have invented computers, smartphones, or the internet. Every computer chip contains billions of transistors, each relying on quantum tunneling, a process where electrons pass through barriers they classically couldn't cross. This purely quantum effect enables the switches that process information at incredible speeds. Lasers are another quantum technology. The word laser stands for light amplification by stimulated emission of radiation. Atoms in an excited quantum state can be triggered to emit photons, which then trigger other atoms, creating a cascade. The result is a coherent beam of light, all photons in step. Lasers are everywhere, in barcode scanners, fiber optic communications, surgery, manufacturing and entertainment. Their precision and power come from quantum mechanics. Magnetic resonance imaging, or MRI, uses quantum properties of atomic nuclei. Placed in a strong magnetic field, nuclei align their spins. Radio waves flip these spins, and as they relax, they emit signals that map the body's tissues. MRI has revolutionized medicine, allowing doctors to see inside patients without surgery. Quantum mechanics also explains chemistry. The bonds between atoms, the shapes of molecules, and the reactions that sustain life all arise from the behavior of electrons in quantum states. The periodic table, the organization of elements by properties, is a quantum phenomenon. Photosynthesis, the process that powers most life on Earth, involves quantum effects. When sunlight hits chlorophyll, it excites electrons, which must navigate to reaction centers efficiently. Recent evidence suggests quantum coherence, where electrons explore multiple paths simultaneously, plays a role. Even more speculative but rapidly advancing is the field of quantum computing. Classical computers use bits, each either 0 or 1. Quantum computers use qubits, which can be in superpositions of 0 and 1. This allows quantum computers to explore many possibilities simultaneously. For certain problems, quantum computers could be exponentially faster than classical ones. They might factor large numbers easily, breaking current encryption. They might simulate molecules precisely, revolutionizing drug design. They might optimize complex systems, from supply chains to financial portfolios. Building practical quantum computers is enormously challenging. Qubits are fragile, easily disrupted by their environment. Maintaining quantum coherence requires extreme isolation, often at temperatures near absolute zero. Yet progress is rapid. Companies and research labs are building quantum computers with dozens, even hundreds of qubits. Quantum cryptography offers unbreakable security. By encoding information in quantum states, two parties can communicate in a way that any eavesdropping is detectable. Attempts to intercept the message disturb the quantum states, revealing the intrusion. Quantum key distribution is already in use for secure communications. Quantum sensors exploit entanglement and superposition for unprecedented precision. Quantum gravimeters measure gravity with extreme accuracy, useful for detecting underground structures or resources. Quantum magnetometers could map brain activity in detail, advancing neuroscience. Even atomic clocks, the most precise timekeepers, rely on quantum transitions in atoms. These clocks are so accurate they gain or lose less than a second over billions of years. They're essential for GPS and scientific experiments testing relativity. Looking ahead, quantum technologies may reshape society. Quantum internet could connect quantum computers across the globe, enabling distributed quantum computing and secure communication. Quantum, materials designed atom by atom using quantum principles, might have properties we can barely imagine. The quantum realm, once thought purely theoretical, has become intensely practical. Every smartphone is a quantum device. Every LED light, every solar panel, every medical scanner owes its existence to our understanding of quantum mechanics. The strange rules of the atomic world, discovered through careful experiments and brilliant reasoning, now power civilization itself. What makes this so remarkable is that we don't need to understand why quantum mechanics works to use it. Engineers design circuits without pondering the measurement problem. Chemists predict reactions without resolving wave-particle duality. The technology works because the mathematics works, even if the interpretation remains mysterious. Yet this practical success also humbles us. We have harnessed quantum mechanics without fully understanding it. We live in a quantum world surrounded by quantum technology, built on quantum principles, and still we cannot say what the quantum realm truly is. The mystery persists even as the applications multiply. Quantum mechanics has been extraordinarily successful for nearly a century. Its predictions have been confirmed countless times. Its applications have transformed technology. Yet physicists still disagree about what it means, about what is really happening in the quantum realm. This disagreement is not about the mathematics or the predictions. Everyone agrees on those. The dispute is about interpretation, about the story we tell to make sense of the equations. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, was the first and remains influential. It says that quantum mechanics describes what we can observe, not an independent reality. Before measurement, a particle doesn't have definite properties. The wave function represents our knowledge, and measurement collapses it to a specific outcome. Bohr insisted that quantum and classical worlds are fundamentally different. Classical concepts like position and momentum have meaning only in the context of measurements. Asking what happens between measurements is meaningless. The Copenhagen interpretation is pragmatic, focused on predictions rather than metaphysics. Einstein despised this view. He believed in an objective reality existing independently of observers. His debates with Bohr are legendary. Thought experiments pitting determinism against probability, realism against instrumentalism. Though Einstein lost the scientific argument, his philosophical concerns endure. The many worlds interpretation, proposed by Hugh Everett in 1957, takes a radically different approach. It says the wave function never collapses. Instead, every quantum measurement causes the universe to split into branches, one for each possible outcome. All outcomes happen, just in different worlds. In many worlds, Schrödinger's cat is both alive and dead, but in separate branches of reality. You see one outcome because you're in one branch, but other versions of you in other branches see different outcomes. The wave function describes not probabilities, but a vast multiverse of parallel realities. Many worlds eliminates the measurement problem by denying that collapse happens. It's mathematically elegant, requiring no special rules for measurement. But it's ontologically extravagant, multiplying universes endlessly. Critics ask, where do these branches exist? Why don't we perceive them? And how do we make sense of probability in a theory where everything happens? De Broglie-Bohm theory, also called pilot wave theory or Bohmian mechanics, offers another alternative. It says particles always have definite positions guided by a quantum wave. The wave evolves according to Schrödinger's equation, while particles follow deterministic trajectories determined by the wave. In this interpretation, there's no collapse and no splitting universes. Particles have real positions at all times, and the apparent randomness comes from our ignorance of initial conditions. The double-slit experiment is explained by the pilot wave guiding particles through one slit while being influenced by both. Bohmian mechanics reproduces all quantum predictions but adds hidden variables, the actual particle positions. It's deterministic and realistic, satisfying Einstein's intuitions. But it's also non-local, particles instantaneously influenced by distant parts of the wave, and most physicists find it cumbersome. Objective collapse theories take yet another approach. They suggest that wave function collapse is a real physical process, not triggered by consciousness or measurement, but by objective criteria. Perhaps when a system reaches a certain size or mass, its wave function spontaneously collapses. These theories modify quantum mechanics slightly, adding collapse terms that become significant for large objects, but are negligible for small ones. They're testable in principle, predicting tiny deviations from standard quantum mechanics. Experiments are underway to search for these effects. Then there's quantum Bayesianism, or cubism, which treats the wave function as representing an observer's personal beliefs about measurement outcomes. Quantum mechanics becomes a set of rules for updating beliefs, not a description of external reality. Different observers can have different wave functions for the same system, and that's okay. Cubism is subjective, even solipsistic to critics. But proponents argue it resolves paradoxes by acknowledging that science is always from someone's perspective. There's no view from nowhere, no God's eye description of reality. Other interpretations abound. Relational quantum mechanics says quantum states are observer-dependent, defined only in relation to other systems. Consistent histories approach quantum mechanics as a framework for assigning probabilities to sequences of events. Each interpretation has its advocates and its critics. What makes this situation so unusual is that these interpretations make the same predictions. They're empirically equivalent, at least for all experiments done so far. The choice between them is partly a matter of taste, of which assumptions seem most reasonable or which questions seem most important. Some physicists are content with this plurality. As long as the math works, they say, interpretation doesn't matter. Others find it deeply unsatisfying. Surely reality is some particular way, even if we can't yet determine which interpretation is correct. The persistence of interpretation debates suggests that quantum mechanics may be pointing towards something deeper, a revision of our concepts of reality, causation, and observation, more profound than any single interpretation captures. Perhaps the quantum realm is telling us that our ordinary categories, built from macroscopic experience, simply don't apply at fundamental levels. Or perhaps future discoveries from quantum gravity or new experiments will finally favour one interpretation over others. For now, the quantum realm remains a landscape of multiple possible meanings, all consistent with the same beautiful but mysterious mathematics. One of the most tantalizing and controversial questions in quantum mechanics is whether consciousness plays a special role. The measurement problem seems to give observers a unique status. Does this mean consciousness causes wave function collapse? Are minds somehow outside the physical laws that govern matter? These questions have attracted attention from physicists, philosophers, and even mystics. Some see quantum mechanics as opening the door to understanding consciousness scientifically. Others dismiss such ideas as misunderstandings of what quantum mechanics actually says. The connection seems to arise from the role of observation. In the Copenhagen interpretation, measurement causes collapse, bringing definite properties into existence. But what counts as a measurement? Does it require a conscious observer, or will any interaction with a macroscopic device suffice? Eugene Wigner, a Nobel Prize-winning physicist, took consciousness seriously. In a thought experiment now called Wigner's Friend, he imagined a person in a sealed lab measuring a quantum system. From inside, the friend sees a definite outcome. But from outside, before Wigner opens the lab, the friend and the system are in a superposition. This leads to paradox. The friend experiences one reality. But Wigner's quantum description includes both possibilities. Wigner suggested that consciousness might be where collapse happens, that only a conscious observation actualizes one outcome from the superposition. Most physicists reject this view. Decoherence theory shows that interactions with the environment, not consciousness, destroy quantum superpositions for large systems. A measuring device becomes entangled with countless air molecules, photons, and atoms, effectively measuring the system without any conscious intervention. Still, decoherence doesn't fully solve the measurement problem. It explains why we don't see macroscopic superpositions, but not why each individual measurement yields one specific outcome, and some argue that consciousness remains mysterious enough that its role can't be ruled out. The many worlds interpretation eliminates any special role for consciousness. Observers are physical systems that become entangled with what they measure, branching along with the rest of the universe. Consciousness doesn't cause splitting. It's just one more physical process subject to quantum laws. Yet many worlds raises its own questions about consciousness. If all outcomes happen, why does your consciousness experience only one? Is there a fact of the matter about which branch you're in, or do copies of you exist in each branch, each convinced they're the only one? Some researchers, like Roger Penrose, propose that consciousness itself involves quantum processes. Penrose suggests that quantum gravity effects in brain microtubules might play a role in generating conscious experience, bridging the gap between quantum and classical realms. This idea is highly speculative and controversial. Most neuroscientists believe the brain operates classically, that quantum effects decohere too quickly in the warm, wet environment of neurons to play any functional role. But the question remains open, a frontier where physics meets neuroscience. Another angle comes from quantum information theory. If consciousness is fundamentally about processing information, and quantum systems process information differently than classical ones, perhaps understanding quantum information is key to understanding mind. Integrated information theory, proposed by Giulio Tononi, suggests consciousness arises from integrated information within a system. Some wonder if quantum entanglement, which creates integrated correlations, might be relevant to consciousness. But so far, no clear connection has been established. The interest in quantum consciousness also stems from the hard problem of consciousness, why subjective experience exists at all. Physical science describes processes and functions, but subjective experience, qualia, seems to be something extra. Some hope quantum mechanics, with its mysteries about observation and reality, might shed light on this puzzle. Skeptics warn against quantum mysticism, the tendency to invoke quantum mechanics to explain anything mysterious without genuine understanding. Just because two things are mysterious doesn't mean they're related. Quantum mechanics is strange, and consciousness is strange, but that doesn't imply consciousness is quantum. What is clear is that quantum mechanics has reshaped our understanding of what measurement means. Observers are not separate from the systems they observe, but become entangled with them. The classical picture of detached, objective observation has been replaced by participatory involvement. Whether consciousness is special in this process remains unclear. Perhaps it is, in ways we don't yet understand. Perhaps it isn't, and the appearance of specialness comes from our anthropocentric perspective. Either way, quantum mechanics has opened new questions about the relationship between mind and matter, questions that continue to fascinate and frustrate in equal measure. For now, the intersection of quantum mechanics and consciousness remains more suggestive than conclusive. It's a space of speculation, of intriguing possibilities, but also of caution. The quantum realm has taught us that nature is stranger than we imagined. Whether that strangeness extends to consciousness itself is one of the great open questions, hovering at the boundary where physics meets philosophy and where science approaches the deepest mysteries of existence. What is real? It seems like a simple question, but quantum mechanics has made it deeply problematic. The theory works magnificently, yet what it says about reality is far from clear. Does the quantum realm exist independently of observation? Or does reality itself depend on measurement? Classical physics assumed an objective reality. Objects have definite properties whether or not anyone observes them. The moon is there when nobody looks. A particle has position and momentum even if we don't measure them. Science was about discovering pre-existing facts about the world. Quantum mechanics challenges this picture at every turn. A particle in superposition doesn't have a definite position until measured. An entangled pair doesn't have separate independent states. The act of measurement doesn't just reveal reality, it seems to participate in creating it. This has led some to question whether quantum mechanics describes reality at all. Perhaps it's just a tool for predicting observations, a mathematical recipe that works without corresponding to anything real. This instrumentalist view treats theories as useful fictions, not true descriptions. Einstein rejected instrumentalism. He believed physics should describe an objective reality, and he viewed quantum mechanics as incomplete precisely because it didn't seem to. His hope was that a deeper theory would restore realism, showing that quantum probabilities arise from ignorance of hidden variables. Bell's theorem, proved in 1964 and tested extensively since, ruled out certain types of hidden variable theories. Any theory reproducing quantum predictions must be either non-local, allowing instantaneous influences across space, or deny realism, rejecting the idea that properties exist before measurement. Most physicists have accepted non-locality. Quantum entanglement creates correlations that cannot be explained by local hidden variables. This doesn't enable faster-than-light communication, but it does mean reality is more interconnected than classical physics allowed. Yet non-locality alone doesn't settle what's real. The many worlds interpretation is deterministic and realistic but multiplies realities endlessly. Copenhagen is non-local but denies that properties exist before measurement. Bohmian mechanics is realistic but adds hidden particle positions to the wave function. Some physicists argue for structural realism. Perhaps what's real is not particles or fields with definite properties, but the mathematical structures and relationships quantum mechanics describes. The wave function itself, or the operators representing observables, might be the true reality, with particles as secondary. Others embrace perspectivalism. Quantum mechanics describes reality from the perspective of an observer, and different observers can have different but equally valid descriptions. There's no single objective description independent of perspective. Reality is relational, defined by interactions between systems. This view draws support from quantum information theory. Information, not matter or energy, may be the fundamental currency of physics. If so, quantum mechanics is telling us that reality is about what can be known, what can be communicated, what differences make a difference. The universe is not made of stuff, but of bits, patterns of information. The holographic principle, emerging from black hole physics, reinforces this idea. It suggests that the information in a region of space can be encoded on its boundary, like a hologram. Three-dimensional reality might emerge from two-dimensional information, implying that space itself is not fundamental. String theory and loop quantum gravity also suggest that spacetime is emergent, arising from more fundamental quantum structures. If space and time themselves are not fundamental, then asking what exists in space and time may be the wrong question. Reality might be something stranger, with space, time, and matter all secondary. These ideas are speculative, but they reflect a growing sense that quantum mechanics is hinting at a deeper revision of our concepts. Perhaps the classical notion of objective reality, with definite states existing independently of observation, is an approximation valid only at large scales. At the quantum level, reality might be contextual, depending on what measurements are made. It might be holistic, with entangled systems forming wholes that can't be reduced to parts. It might be informational, with existence defined by relationships and possibilities, rather than substances with intrinsic properties. This doesn't mean reality is subjective or that we create it with our thoughts. Quantum mechanics is not a license for magical thinking. The theory has precise mathematical rules, and experiments either confirm or refute predictions. Reality pushes back. It has structure and patterns that constrain what we can observe. But the nature of that structure may be fundamentally different from what we assumed. Quantum mechanics suggests that reality is not a collection of objects with definite properties, but a network of potentialities that crystallize into actualities through interaction and measurement. Philosophers speak of ontic and epistemic interpretations. Ontic interpretations say the wave function represents reality itself. Epistemic interpretations say it represents our knowledge about reality. The debate continues, with compelling arguments on both sides. What quantum mechanics has undeniably done is make the question, what is real, a scientific question, not just a philosophical one. The answer matters for how we interpret experiments, design theories, and think about the universe. It's a question that drives research in quantum foundations, quantum information, and quantum gravity. For now, the quantum realm remains tantalizingly ambiguous. It works, it predicts, it explains, but it doesn't tell us clearly what it's describing. Reality, seen through quantum eyes, is richer and stranger than classical physics imagined. Whether it's fundamentally particles, waves, fields, information, or something we haven't yet conceived, remains one of the deepest open questions in all of science. Quantum mechanics is nearly a century old, yet it still feels revolutionary. Its strangeness has not worn off, and its implications continue to unfold. As we look to the future, several frontiers promise to deepen our understanding and extend our capabilities. One of the most exciting areas is quantum computing. Current quantum computers are still in their infancy, noisy and limited in scale, but progress is rapid. Companies like IBM, Google, and startups are building machines with increasing numbers of qubits and improving coherence times. The goal is quantum supremacy, the point where quantum computers solve problems beyond the reach of classical machines. Google claimed to achieve this in 2019, though the claim is disputed. Regardless, practical quantum computing is coming, with applications in cryptography, optimization, drug discovery, and materials science. Quantum algorithms like Shor's algorithm for factoring and Grover's algorithm for search demonstrate quantum advantage. Future algorithms may tackle climate modeling, financial analysis, artificial intelligence, and problems we haven't yet imagined. The quantum computer may become as transformative as the classical computer has been. Another frontier is quantum communication and the quantum internet. Networks of entangled particles could enable ultra-secure communication, distributed quantum computing, and new forms of information processing. Quantum repeaters, devices that extend entanglement over long distances, are in development. China has launched satellites that create entangled photons, demonstrating quantum key distribution between ground stations thousands of kilometers apart. Europe and the United States are investing in quantum networks. Within decades, a global quantum internet may connect quantum computers and enable applications we can barely foresee. Quantum sensors are already pushing the limits of measurement. Atomic clocks, quantum gravimeters, quantum magnetometers all use quantum superposition and entanglement to achieve unprecedented precision. Future sensors might detect gravitational waves more sensitively, map the brain's activity in real time, or discover hidden structures underground. Quantum simulation is another promising area. Quantum computers can simulate quantum systems like molecules or materials more efficiently than classical computers. This could revolutionize chemistry and materials science, allowing researchers to design new drugs, catalysts, batteries, and superconductors atom by atom. In fundamental physics, quantum mechanics continues to probe the nature of reality. Experiments testing Bell inequalities with ever greater precision confirm quantum predictions and rule out ever broader classes of hidden variable theories. Tests of quantum mechanics in new regimes with larger objects, higher energies, and more complex systems may reveal new physics or confirm quantum mechanics in new domains. The intersection of quantum mechanics and gravity remains a major puzzle. Quantum field theory works beautifully but doesn't include gravity. General relativity describes gravity magnificently but isn't quantum. Unifying them is one of the great challenges of physics. String theory, loop quantum gravity, and other approaches attempt this unification. While none has been experimentally confirmed, they offer insights into what a quantum theory of gravity might look like. Future observations, perhaps of black holes, gravitational waves, or the cosmic microwave background, may provide clues. Some physicists pursue tabletop experiments to test quantum gravity. Can gravity create entanglement between objects? Does spacetime have a minimal length, a quantum of distance? These questions might be answerable without building planet-sized accelerators, using precision measurements and clever experimental designs. The measurement problem remains unresolved. Future experiments might test objective collapse theories, which predict deviations from standard quantum mechanics for large objects. Creating and maintaining quantum superpositions of ever larger systems might reveal where the boundary between quantum and classical truly lies. Interpretations of quantum mechanics may also evolve. As quantum information theory, quantum computing, and quantum foundations advance, new perspectives emerge. Perhaps a future generation will look back and wonder why the interpretation question seemed so difficult, having found a framework that makes everything clear. Or perhaps the question will remain open, a reminder that the quantum realm is fundamentally mysterious, resistant to simple stories. Either outcome would be profound, teaching us either that reality is stranger than we can know, or that understanding can eventually penetrate even the deepest mysteries. Beyond applications and theory, quantum mechanics is changing how we think about nature. It's teaching us that reality is non-local, contextual, and informational. It's showing us that observation is participation, that separability is an illusion, and that the classical world of definite objects is an approximation. These lessons extend beyond physics. They influence philosophy, reshaping debates about determinism, realism, and knowledge. They touch on consciousness, raising questions about the role of observers and the nature of mind. They even inspire art and literature, as the strangeness of the quantum world captures human imagination. As quantum technologies become more common, society will face new challenges. Quantum computers might break current encryption, requiring new cryptographic methods. Quantum sensing might enable surveillance in new ways, raising privacy concerns. The quantum internet might create new forms of inequality between those with access and those without. These are not just technical issues, but ethical and political ones. As quantum mechanics moves from laboratories into daily life, we'll need to think carefully about how to use these powerful tools responsibly, ensuring that quantum technologies benefit humanity broadly and don't concentrate power in a few hands. Looking further ahead, quantum mechanics may reveal even deeper layers of reality. Perhaps the quantum realm itself is emergent, arising from more fundamental structures. Perhaps the universe is at its core a quantum computer, processing information according to rules we're only beginning to grasp. Whatever the future holds, quantum mechanics has already transformed our world and our understanding. From atoms to algorithms, from philosophy to technology, the quantum realm shapes everything. Its strangeness is not a flaw, but a feature, pointing us toward truths that transcend our everyday intuitions. The journey into the quantum realm is far from over. Each discovery opens new questions. Each application enables new explorations. The quantum future is bright, filled with possibilities as strange and wonderful as the quantum world itself. We live in a quantum universe. Every breath you take, every thought you think, every color you see, emerges from quantum processes. The electrons in your neurons, the photons entering your eyes, the atoms bonding in your cells, all obey quantum rules. Yet we don't perceive the quantum world directly. Our senses evolved to navigate the macroscopic realm, where quantum effects are hidden by decoherence and averaging. A thrown ball follows a definite path. A chair has a definite position. The everyday world seems classical, solid, and predictable. This classical appearance is an illusion, or rather an approximation. Underneath, the quantum realm churns. Electrons occupy orbitals, probability clouds rather than fixed orbits. Atoms tunnel through barriers, appearing on the other side without crossing the space between. Virtual particles pop in and out of existence, borrowing energy from the vacuum for fleeting instants. The solidity of matter itself is a quantum phenomenon. Why doesn't your hand pass through the table? Not because atoms are hard little balls, but because of the Pauli exclusion principle, a quantum rule that says no two electrons can occupy the same state. When atoms get close, their electron clouds repel, creating the sensation of solidity. Colors are quantum too. When you see red or blue, you're detecting photons of specific energies, emitted when electrons in atoms drop from higher to lower quantum states. The rainbow of visible light is a spectrum of quantum transitions, each color corresponding to a particular energy difference. Chemistry, the science of how substances interact, is quantum mechanics applied to molecules. Bonds between atoms form because electrons occupy molecular orbitals. Quantum states spread across multiple nuclei. The shapes of molecules, their reactivities, their properties, all arise from solving quantum equations. Life itself depends on quantum mechanics. DNA's structure is stabilized by hydrogen bonds, quantum interactions between atoms. Enzymes catalyze reactions by bringing molecules into precise quantum states where reactions are favorable. Photosynthesis captures light using quantum coherence, exploiting superposition to transfer energy efficiently. Your sense of smell may even be quantum. One theory suggests olfactory receptors distinguish molecules not just by shape, but by their vibrational frequencies, a quantum property. When a molecule enters a receptor, electrons might tunnel through it, and the tunneling rate depends on the vibration, creating different neural signals for different smells. The sun shines because of quantum mechanics. Nuclear fusion in its core is possible only because of quantum tunneling, allowing protons to overcome their electrical repulsion and fuse. Without tunneling, the sun would be dark and life on Earth would not exist. Stars forge heavy elements through quantum processes. The carbon in your body, the oxygen you breathe, the iron in your blood, all were created in stellar interiors and supernova explosions. Quantum alchemy on a cosmic scale. Even the early universe was quantum. Tiny quantum fluctuations in the first moments after the Big Bang, stretched by cosmic inflation, seeded the galaxies we see today. The large-scale structure of the universe, the cosmic web of galaxies and voids, traces back to quantum jitters in the primordial fireball, so we are quantum beings, living in a quantum universe, using quantum technology to explore quantum phenomena. Yet the quantum realm remains hidden in plain sight, its strangeness masked by the classical appearance of the world around us. This dual nature, quantum at the core but classical on the surface, shapes how we understand reality. We build theories and models that work at different scales. Quantum, mechanics for atoms and molecules, classical mechanics for everyday objects, relativity for high speeds and strong gravity. Each theory has its domain, and together they describe the universe from the smallest particles to the largest structures. But the boundaries between these domains are not sharp. Quantum effects can persist at surprisingly large scales. Superconductors and superfluids, macroscopic materials that behave quantum mechanically, demonstrate this. So do experiments creating quantum superpositions of molecules and even tiny diamonds. Perhaps the classical world is not separate from the quantum world, but emerges from it through decoherence and complexity. In this view, there's only one world, fundamentally quantum, and the classical is what we see when we zoom out, averaging over countless quantum details. Living in a quantum universe means accepting a certain irreducible strangeness. The universe is not built on the intuitions we develop from everyday experience. It is weirder, more interconnected, more uncertain. Cause and effect, locality, definiteness, all these classical concepts become fuzzy or fail entirely at quantum scales. Yet this strangeness is also a source of wonder. The quantum realm is not a dry set of equations, but a landscape of mystery and beauty. Particles that are waves, objects entangled across space, probabilities that govern outcomes. These are not flaws in our understanding, but features of reality itself, invitations to see the world with fresh eyes. As you lie in bed tonight, consider that your body is a quantum system. The electrons that carry signals in your brain are in superposition, though decoherence collapses these superpositions almost instantly. The atoms in your body are constantly vibrating, their positions uncertain, their momenta uncertain, held together by quantum forces. You're not separate from the quantum universe. You are a part of it, a complex pattern of quantum fields that has learned to think, to wonder, to question. And in questioning, you reach toward understanding using quantum tools, quantum thoughts, to comprehend the quantum realm that gave you birth. This is the quiet miracle of existence, that the universe has become conscious of itself, that quantum processes have organized into structures complex enough to ponder their own quantum nature. You're the universe looking at itself, a momentary arrangement of particles asking what particles are. May that thought bring you peace. You're woven into the quantum fabric of reality, connected to everything through the fields that permeate space, the forces that bind matter, the probabilities that govern outcomes. Rest now, within the quantum realm, part of the mystery you seek to understand. One of the most extraordinary predictions of quantum mechanics is a phenomenon called quantum tunneling. It sounds like science fiction, yet it happens constantly throughout the universe, and even within your own body. Tunneling allows particles to pass through barriers that should be completely impenetrable according to classical physics. It is the quantum realm's way of defying common sense and opening doors that should remain forever closed. Imagine throwing a ball at a wall. In the classical world, if the ball doesn't have enough energy to break through or climb over, it simply bounces back. No matter how many times you throw it, the ball will never spontaneously appear on the other side of an intact wall. The barrier is absolute, and energy conservation is strict. But in the quantum world, things work differently. A particle approaching a barrier has a wave function that extends in space. This wave doesn't stop abruptly at the barrier. Instead, it penetrates into and through it, decreasing exponentially but never quite reaching zero. On the far side of the barrier, there's a small but non-zero amplitude for the particle to appear. What this means is striking. Even if a particle doesn't have enough energy to overcome a barrier, there's still a probability that it can tunnel through to the other side. It doesn't chip away at the barrier or find a gap. It simply appears on the far side as if the barrier weren't there, though the probability decreases rapidly with the barrier's thickness and height. This is not a theoretical curiosity, but a measured, observed, everyday phenomenon. Quantum tunneling is why the sun shines. At the core of the sun, hydrogen nuclei must fuse to form helium, releasing the energy that lights our world. But these nuclei are positively charged and repel each other strongly. The temperature in the sun's core provides energy for collisions, but classically, it's not nearly enough to overcome the electrical repulsion. Quantum tunneling saves the day. The nuclei don't need to have enough energy to surmount the repulsive barrier. They can tunnel through it. The probability is small for any given collision, but with countless collisions happening every second, fusion proceeds at just the right rate to keep the sun burning steadily for billions of years. Without quantum tunneling, the sun would be cold and dark. Earth would be a frozen rock, and life would never have emerged. Every sunrise you see is possible, because particles can do the impossible, tunneling through barriers that should be impassable. Tunneling also explains radioactive decay. Atomic nuclei contain protons and neutrons bound by the strong nuclear force. In some heavy nuclei, alpha particles, clusters of 2 protons and 2 neutrons, are trapped inside by an energy barrier. Classically, they don't have enough energy to escape, but quantum mechanically, they can tunnel out. This is why radioactive materials decay. The alpha particle's wave function extends through the nuclear barrier, and there's a small probability each moment that the particle will tunnel out and escape. When it does, we detect it as radiation. The probability determines the half-life of the isotope, the time it takes for half the nuclei to decay. Uranium-238, for instance, has a half-life of 4.5 billion years. Its alpha particles tunnel through the nuclear barrier so rarely that vast amounts of time pass between decay events for any given nucleus. But across trillions of nuclei, decays happen constantly, powering radioactive dating techniques that tell us the age of rocks, fossils, and the Earth itself. Quantum tunneling is also essential in chemistry and biology. Enzymes, the biological catalysts that make life possible, often rely on tunneling. Protons and electrons can tunnel through energy barriers in chemical reactions, allowing them to proceed at rates much faster than classical chemistry would predict. In photosynthesis, electrons tunnel between molecules in the reaction center, transferring energy with remarkable efficiency. In cellular respiration, protons tunnel through proteins in the mitochondrial membrane, driving the production of ATP, the energy currency of life. Even DNA mutations can occur when protons tunnel between base pairs, shifting the structure and occasionally causing genetic changes. Tunneling is also the basis of one of the most important inventions of the 20th century, the transistor. In semiconductor devices, electrons can tunnel through thin insulating barriers, allowing precise control of electrical current. Modern computer chips contain billions of transistors, each exploiting quantum tunneling to switch on and off billions of times per second. As transistors have shrunk to nanometer scales, tunneling has become both a tool and a challenge. Engineers design devices that use tunneling deliberately, like tunnel diodes and flash memory. But unwanted tunneling, where electrons leak through barriers that should confine them, becomes a problem. Managing quantum effects is now central to electronics design. The scanning tunneling microscope, invented in 1981, uses quantum tunneling to image individual atoms. A sharp metal tip is brought extremely close to a surface. Electrons tunnel between the tip and the surface, creating a tiny current. By scanning the tip across the surface and measuring the tunneling current, scientists can map the atomic landscape with extraordinary precision. This instrument revolutionized nanotechnology, allowing researchers to see and even manipulate individual atoms. It earned its inventors, Gerd Binnig and Heinrich Rohrer, the Nobel Prize. Today, scanning tunneling microscopes are used to study surfaces, design nanomaterials, and explore quantum phenomena at the atomic scale. Quantum tunneling also plays a role in quantum computing. Some proposed designs use superconducting circuits, where quantum information is encoded in states that tunnel through energy barriers. Tunneling allows qubits to switch between states, performing the quantum operations that give quantum computers their power. But tunneling presents challenges too. Unwanted tunneling can cause qubits to lose their quantum state, a process called decoherence. Protecting qubits from tunneling and other sources of decoherence is one of the major obstacles to building practical quantum computers. Engineers must design systems where desired tunneling is enhanced and undesired tunneling is suppressed. The philosophical implications of tunneling are as striking as its practical applications. It shows that the quantum world doesn't respect the classical boundaries we take for granted. Walls are not absolute. Barriers are permeable. Impossibilities become merely improbable. This challenges our intuitions about causation and determinism. A particle tunneling through a barrier doesn't have a continuous path from one side to the other. It doesn't travel through the barrier in the classical sense. It's on one side and then it's on the other, with no well-defined journey in between. Asking how the particle crossed is like asking which slit it went through in the double-slit experiment. The question assumes a classical picture that doesn't apply. The particle doesn't cross in a way we can visualize. It tunnels, a quantum process without classical analog. Tunneling also raises questions about energy conservation. When a particle tunnels through a barrier, it appears on the far side with the same energy it started with. It doesn't borrow energy to climb over, because it doesn't climb. But during the tunneling process, its energy seems uncertain, allowed by Heisenberg's uncertainty principle for brief moments. This interplay between tunneling and uncertainty is deep. The uncertainty principle allows energy to fluctuate for short times, and tunneling exploits this flexibility. The two phenomena are intimately connected, both arising from the wave nature of quantum particles. In cosmology, tunneling may have played a role in the birth of the universe. Some theories suggest the universe itself tunneled into existence from a quantum vacuum, a process called quantum nucleation. In this picture, the universe is the ultimate tunneling event, appearing from nothing or from a pre-existing quantum state through a barrier in the energy landscape. This idea is speculative, but it shows how fundamental tunneling is. If the universe can tunnel into existence, then tunneling is not just a quirk of particles, but a principle woven into the deepest fabric of reality. Quantum tunneling also suggests that reality is more permeable than it appears. Barriers are not absolute but probabilistic. Given enough time, unlikely events become inevitable. A particle trapped behind a barrier will eventually tunnel out, even if the probability is astronomically small. This has strange implications. In principle, quantum tunneling means that even macroscopic objects could spontaneously pass through barriers. The probability is so vanishingly small that it would never happen in the lifetime of the universe, but it's not zero. The laws of physics don't forbid it, only make it fantastically unlikely. This is why you never see baseballs tunneling through walls. The probability depends exponentially on the object's mass and the barrier's thickness. For anything larger than atomic particles, tunneling becomes so improbable it's effectively impossible. The quantum world allows it, but the numbers are against it. Yet at atomic scales, tunneling is routine. It happens constantly in the sun, in radioactive materials, in chemical reactions, in electronic devices, and in biological molecules. It's one of the fundamental processes that make the universe work. Tunneling also offers a glimpse of the quantum realm's generosity. Classical physics is strict, with rigid rules about what can and cannot happen. Quantum mechanics is more forgiving. It offers probabilities, not certainties. It allows possibilities, however remote, for events that classically would be forbidden. This probabilistic nature is not a weakness, but a feature. It makes chemistry rich and complex, with reactions following multiple pathways. It makes nuclear processes possible, powering stars and creating elements. It makes life possible, with enzymes catalyzing reactions through quantum shortcuts. As you think about quantum tunneling tonight, consider that it's happening inside you. Electrons are tunneling through barriers in your cells, protons are tunneling in your mitochondria, particles are doing the impossible to keep you alive. The barrier between possible and impossible is not as firm as it seems. Quantum tunneling is a reminder that the universe is more flexible, more surprising, and more generous with possibilities than our everyday experience suggests. Walls are not absolute. Boundaries are permeable, and the impossible, given quantum mechanics and enough time, becomes merely improbable. One of the deepest questions in quantum mechanics is why the macroscopic world appears classical. If particles can be in superpositions and exhibit wave-particle duality, why don't we see these effects in everyday life? Why doesn't a thrown baseball interfere with itself? Why isn't a cat both alive and dead until we look? The answer lies in a phenomenon called quantum decoherence. It's the process by which quantum systems lose their quantum properties through interaction with their environment. Decoherence doesn't violate quantum mechanics, but rather emerges from it, showing how the classical world arises naturally from quantum foundations. To understand decoherence, we need to think about isolation. In the laboratory, physicists go to great lengths to isolate quantum systems from their surroundings. They cool them to near absolute zero, suspend them in vacuum, shield them from vibrations and electromagnetic fields. Only in such isolation can quantum superpositions and entanglement be maintained. But perfect isolation is impossible. Every system interacts with its environment to some degree. Photons from the surroundings scatter off objects. Air molecules collide with them. The Earth's vibrations jostle them. Each interaction entangles the quantum system with countless environmental particles. This entanglement has a crucial effect. The quantum system's state becomes correlated with the environment's state. Information about the system leaks into the environment, and when information spreads over many particles, it becomes effectively irretrievable. The quantum coherence, the delicate phase relationships that allow superpositions and interference, is lost. Imagine an electron in a superposition of two paths. If the electron is perfectly isolated, the two paths can interfere, creating quantum effects. But if a photon scatters off the electron, the photon carries away information about which path the electron took. The electron becomes entangled with the photon, and the superposition is destroyed. If that photon then scatters off other particles, the information spreads further. Soon, countless particles in the environment carry tiny bits of information about the electron state. Recovering that information to restore quantum coherence would require reversing all those interactions, an impossible task. This is decoherence. The quantum system hasn't collapsed in some mysterious way. It's still described by quantum mechanics, but it has become so entangled with its environment that it effectively behaves classically. The superposition is still there mathematically, but it's distributed across so many environmental particles that it can't produce observable interference. Decoherence happens extraordinarily fast for macroscopic objects. A dust particle in air decoheres in a tiny fraction of a second. A bacterium decoheres almost instantly. Larger objects decohere even faster, because they have more ways to interact with the environment. This explains why we don't see quantum effects in daily life. Not because quantum mechanics stops applying at large scales, but because decoherence is so rapid and thorough that quantum superpositions are destroyed before they can be observed. The classical world is not separate from the quantum world, but emerges from it through environmental entanglement. Schrödinger's famous thought experiment with a cat in a box illustrates the puzzle decoherence solves. According to quantum mechanics, if a radioactive atom is in a superposition of decayed and not decayed, and the decay triggers a mechanism that kills the cat, then the cat should be in a superposition of alive and dead. This seems absurd. We never see cats that are both alive and dead. But decoherence explains why. The cat is a macroscopic object made of countless atoms, constantly interacting with air molecules, photons, and the box itself. These interactions immediately entangle the cat's state with the environment. Even if the radioactive atom is in superposition, the moment its decay affects the cat, that information spreads into the environment. The cat's state becomes entangled with the environment so quickly that the superposition is destroyed long before any human opens the box. The cat is either alive or dead, not because observation collapses the wave function, but because decoherence has already made the state effectively classical. This doesn't fully solve the measurement problem. Decoherence explains why we don't see macroscopic superpositions, but it doesn't explain why we observe one outcome rather than another in a single measurement. In the many worlds interpretation, decoherence causes branching, with each outcome occurring in a different branch. In other interpretations, decoherence is a crucial ingredient but not the complete story. Still, decoherence has transformed our understanding of the quantum classical boundary. It shows that there's no sharp line where quantum mechanics stops and classical mechanics begins. Instead, there's a gradual transition determined by how strongly a system couples to its environment. Small systems, weakly coupled to their surroundings, remain quantum for long times. They can be kept in superpositions, entangled, exhibiting quantum behavior. Large systems, strongly coupled to their environments, decohere rapidly and behave classically. This has practical implications for quantum technology. Building quantum computers requires fighting decoherence. Engineers must isolate qubits from their environment as completely as possible, using techniques like cryogenic cooling, electromagnetic shielding, and error correction codes. Even with these measures, decoherence limits how long qubits can maintain quantum states. Current quantum computers can keep qubits coherent for milliseconds or seconds. For complex calculations, this isn't long enough. Overcoming decoherence is one of the major challenges in making quantum computing practical. Interestingly, decoherence can sometimes be useful. In quantum measurement, coupling a system to a macroscopic measuring device causes rapid decoherence, effectively projecting the quantum state onto a definite outcome. This is how measurements work in practice, through controlled decoherence. Decoherence also explains quantum Darwinism, a theory about how classical reality emerges. According to this idea, only certain states are stable against decoherence. These pointer states are repeatedly imprinted on the environment through interactions. Information about these states becomes redundantly available, which is why multiple observers can agree on what they see. In quantum Darwinism, objectivity, the fact that different observers see the same reality, emerges from the natural selection of robust quantum states. The states that survive decoherence are those that leave the strongest imprints on the environment, making them accessible to many observers. This offers a fresh perspective on why the world seems objective and independent of observers. Not because there's a pre-existing classical reality, but because quantum mechanics itself, through decoherence and environmental interaction, creates consensus about certain observables. Decoherence has also been studied in cosmology. In the early universe, quantum fluctuations were amplified by inflation, but these quantum fluctuations became classical perturbations, the seeds of galaxies. Decoherence likely played a role, with gravitational interactions causing the quantum states to become effectively classical. Understanding this transition from quantum fluctuations to classical structures is crucial for cosmology. It connects the tiny quantum world of the early universe to the large-scale structure we see today. Decoherence may be the bridge between quantum initial conditions and classical cosmic evolution. Philosophically, decoherence challenges the idea that consciousness or human observers play a special role in quantum mechanics. Decoherence happens through physical interactions, not through conscious observation. A dust mote decoheres a quantum state just as effectively as a human scientist. This doesn't eliminate all mysteries. The question of why we experience one outcome rather than another remains. But it shows that the emergence of classical reality from quantum foundations is a physical process, governed by the same quantum mechanics that describes particles and fields. Decoherence also reveals the fragility of quantum states. Quantum coherence is delicate, easily destroyed by environmental interactions. This fragility is why quantum effects are hard to observe and why quantum technologies are challenging to build. Yet it's also why the classical world is stable and predictable. In a universe without decoherence, everything would remain quantum. There would be no stable classical objects, no definite outcomes, no macroscopic reality as we know it. Decoherence is what allows the quantum world to give rise to the classical world, making possible the stable structures that support life and consciousness. As you rest tonight, think about the quantum systems inside you. The molecules in your cells are constantly interacting with their environment, decohering rapidly. Only at the smallest scales, in brief moments, do quantum effects persist. But those moments are crucial, enabling the chemistry that sustains life. Decoherence shows that the boundary between quantum and classical is not a fundamental divide but a practical one, determined by interaction and environment. The quantum realm is always there, beneath the surface, but it's hidden by the veil of decoherence, appearing classical to our macroscopic senses. The universe is quantum through and through. The classical world you experience is not separate, but emerges from quantum foundations through the subtle, swift process of decoherence. It's a reminder that what seems solid and definite is built on a foundation of quantum uncertainty, held together by interactions that are themselves quantum processes. For most of the 20th century, biology and quantum mechanics seem to occupy separate realms. Biology dealt with messy, warm, wet systems where classical chemistry ruled. Quantum mechanics belonged to physics, describing cold, isolated atoms and particles. The two fields rarely intersected. But in recent decades, this separation has dissolved. Scientists have discovered that quantum effects play crucial roles in biological processes. Life, it turns out, has learned to exploit quantum mechanics, using tunneling, superposition, and possibly even entanglement to enhance efficiency and function. This emerging field, called quantum biology, is revealing that living systems operate at the boundary between quantum and classical worlds. They're warm and noisy environments where decoherence should destroy quantum effects almost instantly. Yet life has found ways to protect and utilize quantum phenomena. One of the clearest examples is photosynthesis, the process by which plants convert sunlight into chemical energy. When a photon strikes a chlorophyll molecule, it excites an electron. This excitation must then travel to a reaction center where it drives chemistry. The question is, how does it get there so efficiently? In classical models, the excitation would hop randomly from molecule to molecule, like a drunken walk, often getting trapped or lost. But photosynthesis is remarkably efficient, with nearly 100% of captured photons leading to productive chemistry. This efficiency puzzled scientists for decades. Recent experiments suggest quantum coherence plays a role. The excitation doesn't simply hop from one molecule to another. Instead, it exists in a quantum superposition, exploring multiple pathways simultaneously. By being in multiple places at once, it can find the optimal route to the reaction center. This was discovered by studying photosynthetic complexes with ultrafast lasers, measuring how energy moves on femtosecond timescales. The results showed oscillations characteristic of quantum coherence persisting for surprisingly long times, despite the warm, noisy environment. How can quantum coherence survive in such conditions? Researchers believe the protein scaffolding around the chromophores is precisely tuned to protect quantum states from decoherence. The environment isn't just noise, it's structured in ways that support quantum effects. This is an astonishing discovery. Life didn't just stumble upon quantum mechanics. Evolution shaped biological systems to exploit it, fine-tuning molecular structures over billions of years to maintain quantum coherence just long enough to gain an efficiency advantage. Another example of quantum biology is found in bird navigation. Many birds migrate thousands of miles with remarkable accuracy, and evidence suggests they use Earth's magnetic field as a compass. But how do they sense such a weak field? The radical pair mechanism proposes that birds have specialized proteins in their eyes, containing chemical radical pairs, molecules with unpaired electrons. When light hits these molecules, it creates radical pairs whose electron spins are entangled. The Earth's magnetic field affects these spins differently depending on the field's orientation. This quantum mechanical process produces different chemical products depending on the magnetic field's direction. The bird's brain interprets these chemical signals, effectively sensing magnetic direction. The mechanism requires quantum coherence to persist for microseconds, long enough for the chemical reactions to complete. Experiments with robins show that their magnetic sense is disrupted by certain wavelengths of light and by radio frequency fields that should affect quantum spin states. This supports the quantum model and suggests that birds literally see magnetic fields through quantum effects in their eyes. Quantum tunneling is ubiquitous in biology. Enzymes, the catalysts that speed up biological reactions, often rely on tunneling. Protons and hydrogen atoms can tunnel through energy barriers, allowing reactions to proceed at rates that classical chemistry cannot explain. In some enzymes, the rates are enhanced by factors of thousands due to tunneling. This is crucial for life because many biological reactions would be far too slow without it. Metabolism, DNA replication, cellular respiration, all depend on enzyme-catalyzed reactions that exploit quantum tunneling. Olfaction, the sense of smell, may also involve quantum effects. One theory suggests that olfactory receptors don't just recognize molecular shapes, but also detect molecular vibrations. An electron tunnels through a molecule in the receptor, and the tunneling rate depends on the molecule's vibrational frequency. Different molecules vibrate at different frequencies, creating different tunneling rates and different neural signals. This would explain why molecules with similar shapes but different vibrations smell different. Experiments with deuterated molecules, where hydrogen is replaced by heavier deuterium, show that some smells change, supporting the quantum vibration theory. DNA mutations might also have quantum origins. The structure of DNA depends on hydrogen bonds between base pairs. Protons in these bonds can tunnel from one position to another, changing which bases pair together. If this happens during DNA replication, it can cause a mutation. Most such mutations are corrected by cellular machinery, but occasionally they persist, contributing to genetic variation and evolution. Quantum tunneling in DNA might be one of the sources of the genetic diversity on which natural selection acts. Even consciousness, the deepest mystery of biology, has been linked speculatively to quantum mechanics. Roger Penrose and Stuart Hameroff proposed that quantum processes in microtubules, protein structures inside neurons, might play a role in consciousness. They suggest that quantum computations occur in microtubules, and that collapse of the quantum state corresponds to moments of conscious awareness. This theory, called orchestrated objective reduction or ORCOR, is highly controversial. Most neuroscientists are skeptical, arguing that the brain is too warm and noisy for quantum coherence to persist. But the theory continues to inspire research at the intersection of quantum mechanics, neuroscience, and philosophy of mind. Whether or not consciousness is quantum, the broader lesson of quantum biology is clear. Life has evolved to use quantum mechanics. Natural selection has discovered and optimized quantum effects over billions of years, incorporating them into the machinery of living cells. This has profound implications. It suggests that quantum mechanics is not just a feature of the microscopic world, but plays functional roles at the level of organisms. Birds navigate, plants harvest light, and enzymes catalyze reactions all more effectively, because evolution has harnessed quantum phenomena. It also means that biology may teach physics new lessons. Biological systems maintain quantum coherence in warm, complex environments in ways that physicists are only beginning to understand. Studying how life does this might inspire new quantum technologies, like room temperature quantum computers or more efficient solar cells. Quantum biology also challenges the classical reductionist view that living systems can be fully understood through chemistry and molecular biology alone. While chemistry is quantum mechanical, most biological models treat molecules as classical objects. Quantum biology shows that quantum effects at the smallest scales can propagate upward, influencing function at higher levels. This doesn't mean life violates physical laws or requires new physics. Quantum biology uses standard quantum mechanics. But it shows that the quantum realm extends further into the biological world than previously thought, blurring the boundaries between the quantum and the classical, the physical and the biological. As you lie in bed, quantum processes are occurring throughout your body. Electrons are tunneling in your mitochondria, generating ATP. Proteins in your retinas are undergoing quantum reactions in response to light. Enzymes in your cells are catalyzing reactions through quantum effects. You're not just a classical machine, but a quantum biological system, a complex interplay of classical and quantum processes working together. The quantum realm is not external to life, but integral to it, woven into the very fabric of biology. This unity between quantum mechanics and life is one of the most beautiful discoveries of modern science. It shows that the strange rules of the quantum world are not esoteric abstractions, but practical tools that life uses every day. The quantum realm and the living realm are not separate but intimately connected, part of a single, unified reality. From the earliest experiments with light and atoms to the latest quantum computers and sensors, we have traced a journey into the heart of reality. The quantum realm has revealed itself through careful observation, brilliant reasoning, and technologies that turn quantum strangeness into practical tools. We have seen how quantum mechanics emerge from the puzzles of blackbody radiation and the photoelectric effect. We explored wave-particle duality, the uncertainty principle, entanglement, and the measurement problem. We examined quantum field theory and the particle zoo, quantum technologies that shape modern life, and the diverse interpretations that attempt to make sense of it all. We have pondered the relationship between quantum mechanics and consciousness, questioned what is real, and looked toward a future where quantum technologies may transform society. We have recognized that we live in a quantum universe, our very existence dependent on quantum processes. And yet, after all this exploration, the central question remains: what is the quantum realm? Is it a description of nature's fundamental behavior, or a framework for calculating probabilities? Is the wave function real, or just a mathematical tool? Do particles have properties before measurement, or does measurement create reality? Is the universe deterministic with hidden variables or truly probabilistic? Does consciousness play a special role, or is it just another physical process? These questions do not have agreed-upon answers. Nearly a century after quantum mechanics was developed, physicists still debate interpretations. The theory works magnificently, but what it means remains contentious. Perhaps this is the quantum realm's deepest lesson, that nature is more subtle than our categories, more mysterious than our explanations, more interconnected than our intuitions suggest. The quantum world resists simple stories, refusing to conform to classical expectations, or perhaps we're still missing something, a deeper principle or theory that will make everything clear. Maybe future generations will look back and see quantum mechanics as we see classical mechanics, a valuable approximation to something more fundamental. Either way, the quantum realm stands as one of humanity's greatest intellectual adventures. It has taken us from confident classical certainty to profound quantum mystery. It has shown us a universe where observation matters, where separability fails, where definite states are replaced by superpositions and probabilities. This revolution in understanding has been matched by a revolution in capability. Quantum mechanics has given us the transistor and the laser, MRI machines and solar cells, and promises quantum computers and quantum networks that may reshape civilization. The quantum realm is both utterly abstract, equations and principles that seem divorced from experience, and intensely practical, the foundation of modern technology. It is both solved, with precise mathematical rules that predict experiments, and unsolved, with philosophical puzzles that challenge our deepest assumptions. As you drift toward sleep tonight, let your mind wander through what we have explored. Imagine particles that are waves, objects entangled across space, measurements that create reality. Picture the quantum foam at the smallest scales, virtual particles flickering in and out of existence. Think about the electrons in your brain, the photons that brought you images today, the atoms that make up your body. You are a quantum being, thinking quantum thoughts in a quantum universe. The mystery surrounds you, sustains you, and in a profound sense, is you. Every heartbeat is a quantum process. Every breath involves quantum transitions. Every moment of consciousness emerges from quantum interactions in neurons. The quantum realm is not somewhere else, not a distant abstract domain studied only by physicists. It is here, now, in everything. It is the fabric beneath the fabric, the reality beneath appearances, the strangeness within the familiar. And perhaps that is enough. Perhaps the quantum realm does not owe us an explanation that satisfies our classical intuitions. Perhaps it is simply showing us the way things are, inviting us to expand our conception of reality, to embrace mystery alongside understanding, to accept that the universe is richer than any story we can tell about it. The ancient philosophers wondered about the nature of matter and reality. Newton gave us a clockwork universe of certainty and determination. Einstein showed us that space and time are relative and that reality is stranger than we thought. And quantum mechanics has taken us further still, into a realm where even the questions become uncertain. This is not a failure of science, but a triumph. We have pushed understanding to the point where our concepts strain and stretch, where new ways of thinking become necessary. The quantum realm marks the frontier where human knowledge meets the unknown, and that frontier is moving forward, always offering new mysteries, new technologies, new insights. So rest now, knowing that you have glimpsed something profound. The quantum realm remains mysterious, but you have walked its contours, from philosophical foundations to practical applications, from particles and waves to interpretations and implications. Tomorrow you will wake in a quantum universe, surrounded by quantum devices, your body performing quantum processes. The mystery will remain, but you will carry a deeper appreciation of the strangeness that underlies everything. May you find peace in the knowledge that reality is more wonderful than we imagined, that science is a journey without end, and that the quantum realm, however mysterious, is not separate from you but the very ground of your being. Sleep well within the quantum foam, the field of possibilities, the fabric of reality itself. The universe holds you gently, as it always has, in the quantum embrace that gives rise to stars, to planets, to life, to consciousness, to wonder. Good night.